All right, so welcome to the final video for Module 3, which is Chapter 2, our chemistry chapter. We're going to finish this module talking about some elements that make up the human body. So what are the more common elements, the major elements? And then we're also going to focus on water as an important factor and component of living organisms. So as we saw in the first video, there are a lot of elements that occur naturally on the globe or on Earth. There's close to 100 different naturally occurring elements, but out of those 100, there are only 6 that make up 99% of our body weight. Those 6 are oxygen, carbon, hydrogen, nitrogen, calcium, and phosphorus. So those are the big 6. The remaining 1%, right, comes from some trace elements and then some micro elements. Right? So like potassium, sulfur, sodium, chlorine, magnesium, iron. Right? This make up like the remaining 1%. Okay? And so so basically what I want you to know from that are these big 6. So the big 6 that make up 99% of our body weight. Was also another big component of our body, which comes from 2 of those elements, oxygen and hydrogen, is water. So water is a really big property of living organisms, and water makes a lot of things possible in living organisms. Water, one, is an excellent solvent. So it can dissolve a lot of ions, a lot of molecules. Water is also liquid at body temperature, which is important. It can absorb and also hold heat energy, and it can help regulate heat energy through the evaporation process. And then water is also really important for chemical reactions, as we've seen, especially in like your dehydration, synthesis, and hydrolysis reactions, right? All of those are based around using or losing water. Now, when we say water is a biological solvent, we mean that water is a substance that can dissolve other substances. So it's basically a liquid that can dissolve a lot of other substances and molecules. And so any liquid that dissolves substances is known as a solvent. Anything that is dissolved in a solvent is called a solute. So any dissolved substance is known as a solute. We've already talked a little bit about hydrophilic and hydrophobic, but just to reiterate, hydrophilic are polar molecules that are attracted to water, so they like water. Hydrophobic are non-polar molecules that do not like water. They don't interact with water. Okay? So hydrophilic is polar, hydrophobic is non-polar molecules. So here we have an image where we have salt crystal in a water solution. You can see all of the water molecules that look like the little Mickey Mouse heads. And then you have your salt crystal, which is made up of your chlorine and your sodium ions. And remember, there's polarities to those ions. Sodium is positively charged, chlorine is negatively charged. So that means that the water molecules are going to interact with those individual ions, and they'll actually kind of pluck these sodium and chlorine crystals out of that, or ions out of the crystal, and dissolve it in the water, because the negative areas of the water molecule, which are the oxygen atoms, will bind to the sodium atoms and pull it out, whereas the positive hydrogen atoms will associate with the negative chlorine atoms and pull them out into solution. And so this is why water is really good at dissolving things, because it has that partial polarity. Now, we also mentioned that water is liquid at body temperature. So water serves as a very important transport mechanism in the blood, which is 90% water. If water wasn't liquid at body temperature, this wouldn't be the case. And it also makes up the spaces that are inside of our cells and also outside of our cells, so the intra and extracellular spaces. And because of this, 60% of our body weight is water. Okay. Now, we also mentioned that water helps to regulate body temperature. So, water can absorb and hold a large amount of heat, and it can take up a lot of heat by only increasing a relatively small amount. And what that does is it prevents rapid changes in body temperature. And so we can take up a lot of heat and only change our temperature very small increments. But what that also means is that if we have water on the surface of our body, that water can take up a lot of heat, and then it will break the bonds within those water, and then that water molecule will be released into the atmosphere as it evaporates, and the energy from our body, the heat from our body, will have been lost to break the bonds between those water molecules, and so we can lose that heat as evaporative cooling. And so we can lose that excess heat relatively quickly. Excuse me. And then finally, water also participates in chemical reactions. And so we've seen this in our previous video where we talked about how it's used to make carbohydrates, proteins, lipids, and how it's also used to break down those molecules as well. Now, in water, water can have a concentration of hydrogen ions. And the amount of hydrogen ions that is found in the water determines its pH. And so it determines whether or not the water is acidic or whether or not it's basic or alkaline. And so a molecule is referred to as being acidic or an acid molecule if it can give off a hydrogen ion in solution. And so if it gives off hydrogen ions, then it increases that hydrogen concentration in the water solution. If it is an alkaline or a base molecule, it will pick up hydrogen ions when it's put into solution. So it removes hydrogen ions from the aqueous solution. So it decreases that concentration of hydrogen ions in solutions. So if water has more hydrogen ions, then it is acidic. If it has less hydrogen ions, then it's a base. Now we can measure the concentration of hydrogen ions by using a pH scale. And so if you measure the amount of ions, hydrogen ions in water, and you convert it to the pH scale, the pH scale has a value of 0 to 14. So if we measure the hydrogen ion concentration in water and it has a pH of 7, then it's neutral. That basically means that the hydrogen ion to OH ion concentration is equal. If it's acidic, then you have more hydrogen ions, and if it's basic, you have less. So pH of 7 is neutral, so they're equal. A pH less than 7 means that hydrogen ions are increasing. A pH of greater than 7 means that the hydrogen ions are decreasing. So 7, so we should say like 7.1 to 14 is basic, and then 0 to 6.9 is acidic. Okay. So here's an example of a pH scale. So 7 is neutral. So that's like our human blood and our tears. Acidic solutions are like lemon juice or any citrus, vinegar, your soda, and then things like hydrochloric acid, tomatoes. Alkaline solutions are like cleaning materials, so like ammonia, Drano, bleach, baking soda. So all of those are like your alkaline substances. And one thing that I want to mention is that the pH scale is a log scale, right? So it's log. Okay, so basically that means that every one change in the pH scale is a 10 times change in hydrogen ions. Okay, if you go up in the pH scale, you decrease in hydrogen ions by 10 times. If you go down on the pH scale, you increase in hydrogen ions by 10 times. And that's 10 times every step you change on the pH scale. So for example, let's say we have a pH of 5. Let me actually erase. Let's say we have a pH of 5. Okay. And that pH of 5 contains 10 hydrogen ions. Let's say we change the pH to 3. Okay. If we change the pH from 5 to 3, what is the concentration of hydrogen ions at a pH of 3? Okay. So take a minute, try to figure that out. Pause the video. All right. So hopefully you realize that, okay, we can figure this out because if we know that if we're changing 10 times the hydrogen ion concentration for every one change in the pH scale, we can just do a conversion. So basically we're moving two levels on the pH. So we're going from 5 to 3. So we're saying 10 times 10 is 100. So we're changing the ion concentration 100 times, okay? And we're decreasing in pH, so that means that hydrogen concentration is going up. So basically, we would say 100 times 10, we would be at a concentration of 1,000. Okay? Now, if we went to a pH of 7, right, we would go down 100 times because as we increase in pH, right, you decrease hydrogen ion concentration. So if we start out at 10, we basically just move our decimal, right, 2 places. So we would go 1, 2, so we would be at 0.1 hydrogen ion concentration. Okay, so that's the big thing, is that the pH is a log scale. You're changing by a factor of 10 every pH scale that you change, right? So 10 times, 10 times, right? 10 times. So if you change from an 8 to an 11, that's 3 steps. So it's essentially 10 to the third. So that is a 1,000 times change. Okay? And it would be a decrease in hydrogen concentration because we are increasing in pH. If we went from 6 to 3, it would be a 1,000 times change, but it would be an increase because we are becoming more acidic. Okay? Now our bodies can produce buffers that minimize the change in pH. And so buffers help maintain a stable pH in our body fluids, because remember we said that enzymes need a stable pH to work properly. And so our bodies can release either carbonic acid or bicarbonate to act as buffers, okay? And so what basically happens is if you eat something acidic, then your body is going to release bicarbonate, which is HCO3, and that bicarbonate will take up the hydrogen ions to increase the pH and make it less acidic, because the hydrogen ion concentration will go down because they will be tied up into these bicarbonate molecules. When that hydrogen ion grabs onto the bicarbonate, it turns into carbonic acid. Now and so let's say our blood is becoming alkaline or basic, and we need it to go down in pH. And so our bodies can then release carbonic acid that would release a hydrogen ion. So it would give off a hydrogen ion and turn into bicarbonate, and the blood would become more acidic. Right? So if the blood is too acidic, you get bicarbonate, again, picking up those ions, making carbonic acid, lowering the hydrogen ion concentration. And then if it's too alkaline, you get carbonic acid to be released, which disassociates, releasing a hydrogen ion and leaving bicarbonate as a product. Okay? So those are very important as buffers, carbonic acid and bicarbonate, to help maintain homeostasis in our pH levels in our body. All right, so we'll finish this chapter and finish this video with a final animation that discusses properties of water.
Life is based on water, primarily because of water's solvent properties. Understanding this and the other properties that make water so important means understanding water's molecular structure. Water is a solvent for many of the molecules in living organisms, primarily because it's a polar molecule. This means that electrons shared by the hydrogen and oxygen atoms are more attracted to the oxygen than to the hydrogen. This unequal attraction of electrons generates partial electric charges within the water molecule. The oxygen atom has a partial negative charge, and the hydrogen atoms have a partial positive charge. Therefore, a water molecule as a whole has positive and negative ends. The molecule is polar. When two liquid water molecules approach each other, the partially negative oxygen atom of one water molecule is attracted to the partially positive hydrogen atom of the other water molecule. Hydrogen bonds form between water molecules, causing them to stick together. These same hydrogen bonds form between water and other molecules that carry charges. Here's an example of how water acts as an efficient solvent of table salt or sodium chloride. Water molecules surround the sodium and chloride ions of salt. The oxygen atom in each water molecule, with its partial negative charge, bonds to a positively charged sodium ion. The hydrogen atoms of the water molecule, with their partial positive charges, bond to the negatively charged chloride ions. Water's polarity makes it an effective solvent for charged or polar solutes. The hydrogen bonds that form between water molecules are responsible for one of water's most unusual properties. Although solids are usually denser than liquids, water expands and becomes less dense as it changes from a liquid to a solid. This property allows ice to float on water. Let's examine why ice floats on water. In ice, each water molecule forms 4 hydrogen bonds with 4 adjacent water molecules, giving the ice an ordered lattice structure. In this structure, the hydrogen bonds overcome the motion of the individual water molecules, holding them in a fixed 3-dimensional pattern. In addition, the water molecules are spaced farther apart, making ice less dense than water. As ice melts, hydrogen bonds are broken, and the water molecules are free to move closer together, forming liquid water. Liquid water, therefore, is more compact or denser than ice. What would be the implications for life if ice were denser than liquid water? The hydrogen bonds between water molecules are also responsible for another unusual property of water. A great deal of heat energy is required to change water's phase or state from solid, ice, to liquid, or from liquid to gas, steam. Water has an extraordinarily high heat capacity, meaning that it can absorb a great deal of heat before it increases in temperature. Water's heat capacity is unusually high because it contains many hydrogen bonds. A large amount of energy is needed to break the hydrogen bonds between the molecules before the temperature of the water rises. Although liquid water is denser than ice, the molecules in liquid water move more freely. When liquid water has absorbed enough energy to break all of the hydrogen bonds, it changes from a liquid to a gas, steam. Sometimes a water molecule dissociates or breaks up, forming a positively charged hydrogen ion and a negatively charged hydroxide ion. In any sample of water, the fraction of water molecules that are dissociated is extremely small, so water molecules are much more common in the human body than are hydrogen and hydroxide ions. Substances called acids and bases influence the concentration of hydrogen ions in solutions. An acid, such as hydrochloric acid or HCl, releases hydrogen ions when placed in water. A base, such as sodium hydroxide or NaOH, produces hydroxide ions when placed in water. The hydroxide ions produced when NaOH dissociates reacts with hydrogen ions to form water molecules and thus reduces the concentration of hydrogen ions in solution. Therefore, acids increase the concentration of hydrogen ions in solution, and bases decrease the concentration of hydrogen ions in solution. The measure of the hydrogen ion concentration in a solution is called its pH. The pH scale ranges from 0 to 14. A pH of 7 is considered neutral, as the substance does not increase hydrogen or hydroxide ions. A pH of less than 7 is acidic, and a pH of greater than 7 is basic. Oven cleaner, ammonia, and baking soda are basic. Human blood is nearly neutral. Urine, beer, and battery acid are acidic. Usually, the amount of hydrogen ions in a solution is very small. For example, the concentration of hydrogen ions in beer is 10 to the minus 3 moles per liter, which is only 0.001 moles per liter. Each reduction of pH by 1 unit represents a 10-fold increase in the amount of hydrogen ions. So a solution with a pH of 2 is 10 times more acidic than a solution with a pH of 3.
All right, so that does it for this video and for the chapter. So that's it for our chemistry chapter. So the next module will be the cell module, which is module 4, I believe. And so as always, let me know if you have any questions, any concerns, or any issues with any of your assignments, and we'll see you in the next module.